Now we are going to see that one thumb instruction set, right? So the last class we discussed about the ARM instruction set. Now we are going to see thumb instruction set. THUMP thumb instruction set. The difference between ARM and thumb is ARM instructions are 32-bit size. The instruction itself 32-bit size. So we are having now the add yes with the R0, R1 and R2. Then we are having logical shift left with some number. So this is one instruction. So this instruction is going to be coded with 32-bit. So this is the instruction where we are having now that add s is one opcode. Then we are having R1, R0 is one register. For that we are having one value. Then R1 and R2 and logical shift left. So the around 0 to 31 bit is covered now. So we are having one ASCII value for 0 to 31 belongs to that particular instruction. Right. Now, if you are having thumb instruction, the thumb instruction is only 16 bit. So we are having limited size. So half of that size. So this is ARM instruction set. ARM instruction is 32 bit. Thumb instruction is 16 bit. Now, here we see that what's the difference and something, right? So what's the purpose of the thumb is we are having has higher code density. So the important point is code density. So what you mean by that one is here if you are writing one program with the ARM instruction set, so we are having this is the ARM instruction set. So if you are on 10 line of code, so we are having 32 bit plus 10 line. So we are having 320 bits are required. If you are writing the same program with equivalent program, we can write that program with around 14 line. 14 line of code we can have now the same equivalent program. So this is the one program. The same program we can written in thumb instruction. This is ARM instruction. Now the same program we can written in thumb instruction with 14 line of codes, right? So the line of code is more. Then we can have now 14 line of code. So 14 into 16. So the total 14 into 16 is right. Right here. Right. Now here we are having 14 into 16, right? So we are having 16 is so we are having now 224 bits are required. 224 bits are required. Here we are having 320 bits. So now we are having now the density is high. So higher code density we can have now using thumb instruction sets. Right? If you can write a program in thumb instruction set, you write that in thumb instruction set, then it will be having that the size of memory for storage, right? So we are having 224 bits only. Here we record 320. Both are same execution. So we are having now the program is equivalent, but we can have now the high density of the code using thumb instruction set. Now you see this one, almost around 30%. We can have now less size. So here we will consider now 320 to 224, right? So we are having minimum 30% we are having now the code density is going to have now. So we can record the less memory for storing the program. Now here another one the important point is the arithmetic shift, logical shift left right we can't write. So it is a separate statement. So separate instruction for the DAs, right? So in that ARM instruction we can have now that one as add yes R0, R1, R2 and logical shift left with the hash 2, right? So this is we are having now. So in that particular 16 bit this much of information is not enough. We can't put it in 16 bit. So we are having now the less, right? So up to this one. So we can have now the two registers or 3 registers. So we can have now, right? Now we'll see that how we are going to have now. So arithmetic shift, logical shift left within the single statement is not possible. Now here you see this simple example, right? So suppose they may ask question, right? So how the thumb code is having code density is a simple example, right? Now we are having the division. division program, right? So we are having add greater than. Okay. So we are having a divisor and a dividend, right? Okay. Now we are having now that we are having a program for divide the number, right? Move that R naught 3 is 0. Initially we are having that divide is 0. Then we are having now that R naught is having that value. Then R2 is having that R1 is having divisor. So we want to divide that one, right? So now what we have to do, R0 to R1 we have to subtract. Then we are getting now that result. Then we are having now add, suppose we are having that greater than that one, we have to add that one, right? Or otherwise we have to give that branch and greater than or equal to, then it will go to the loop, right? We have to subtract repeatedly. So we are adding that R3. So we are having this is a add greater than or equal, right? So that one time division, two times division, like we can subtract one time subtraction, two repeated subtraction we are doing now that division, right? So there is no direct division instruction. So you have to do that repeated subtraction, right? So we are having that value here in R0. So for example, you will have that one. The R0 is having that value 80. Then R1 is having that value 5. 80 20, we will put that 20 80 20, right? Now here we are having now that 80 20, one time we are subtracting, we are getting now 60. So that one as we are adding 1, so one time we are subtracting. Then we are having greater than or equal to, it will go to the loop. Then next time we are subtracting 60 minus 20. So here we are getting now that increment by 1 2. So we are having now 40. Then 40 once again, then it will go for subtract 20 3. Then once again we are subtracting, we are getting now 4. Now we are subtracting, then we can't get now. So we are having now, this is in the negative value. So once again, then you have to add that one for getting revert back that value, right? So we are having, this is the divisor, right? So this is a we are having now, this is divide. Then the remainder is R2. So that one is here we are having that R2 is in the remainder. So this is the program. Right. Now here we are having now the same program. We can return in thumb mode. So thumb mode is here we are having 16 bit, right? So move R0, move R3 comma 0. So initially the R3 is going to have that 0. So we are getting the result in the divide. So we are having now initialize the R3 as 0. So we are getting now the result in the, so R3 is making now as initialize as 0. Now we are adding R3 is 1. Then we are subtracting that one R0 and R1. So only two registers we can have now maximum, right? So R0 and R1, we are getting now the result in R0. Then we are having greater than or equal to, it will go to the loop. Then subtract that R3 by 1, right? So here we are having less than that one. Then we have to subtract 1, right? So it will go to up to 5. Then we are subtracting 1, we are getting up to 4, right? Then we are having, if it is going the negative value, once again we are adding, we are getting now the original value, right? Then we are getting that instruction, right? So now you will see that one. This is we are having now 1 2 3 4 5 5 line of codes, 5 into 4 bytes, so total 20 bytes are there. Here we are having now 6 line of code, 1 2 3 4 5 6 6 line of code. Each one is 2 byte, 16 bit, so the 12 byte. So we are having 20 byte memory is required. Here we are having 12 byte memory required. Both are having the same result. Both are having same result. So if the register is using 32 bit only, then both are having same result. Okay. Once again I will tell that one. So this is another one important case. They will ask that question something, right? So now you assume that one. We are having now that value is R0 is 62, right? So we are assuming that one. R0 is having that value as 62. Then R1 is having that value as 20, right? We are assuming that, right? Now here we are having now 62 minus 20. So we are getting now that 42. Then it is one time we are having R3 is added with 1. So one time we are subtracting. Then we are having greater than or equal only. So greater than or equal. So we have to branch greater than or equal to loop. So it will go to the loop. Then once again, then we are subtracting the 42 minus 20. We are getting now 22. So that increment by 1, right? So that the 1 is going to have as 2. Next we are having now that once again 22 minus 20, we are getting now that 2, right? Then next time we are adding now. Next we are having now 2 minus 20. So that is we are going to have the negative value. So that this condition is not satisfied. This condition is not satisfied. Now we are getting now that this is minus 18. So the minus 18 is added with once again 20. We are getting now the remainder. So the remainder is 2 now. So this is the execution, right? The same execution we are going to have now through thumb instruction set. Clear? Srilekha?
Sir, yes, sir.
Okay. So this is we are having now for a simple example for port density. Now you have to suppose they may ask you arm instruction and thumb instruction. What's the difference between these two? So you have to give one simple example. Right. Now here we are having now the arm instruction, right? So we are having now this is the thumb instruction. The thumb instruction is going to have that one as arm instruction. Now here how do we make that one as? So add yes R0 and R0 plus 3, right? So that is we are having now R0 content plus 3 is added. We are getting now that R0, right? So here we are having R0 is there. Then we are adding that within that R0 we are adding 3. So we are getting now, right? So this is the case we are having now. We can have now the equivalent that thumb instruction. We are having the equivalent arm instruction is this one, right? So we are having now this is thumb instruction. So thumb instruction is showing now as 3. So arm instruction is going to thumb instruction is going to have as arm instruction, right? Now here directly we'll go for the thumb instruction, right? So what are the possible instructions? So that this is actually I told you that one the subset of arm instruction. So we can have now add with the carry. So that add with carry is there. We are having now the same instruction as add with carry, and we can have a add and instruction. Then we are having the separate arithmetic shift register instruction, right? So that ASR actually in that thumb arm instruction we can have now that extended, right? So that is we are having add as add yes, we are having R0 and R1 and R2. Then we can have now arithmetic shift right. Arithmetic shift right with that 2 we can have now. But here we are having this arithmetic shift right is separate instruction. Then we are having bit instruction, right? A bit like branch instruction. B is branch instruction. The same way we are having now as branch instruction. Next we are having bit clear instruction. We can have now breakpoint instruction, right? Breakpoint instruction and branch with link instruction, branch with link and exchange, branch with exchange instruction, right? So that is as like that thumb arm instruction set we are having now. Then compare negative and compare instruction. Then exclusive OR instruction, load multiple register, load single register, logical shift left is one instruction, and logical shift right is another instruction, right? In that case of ARM, these are all the comes under that single instruction. So this is not a separate instruction. Here we are having now this logical shift left and logical shift right is a separate instruction. So you have to do that logical shift and then we have to do that addition operation. Next one is we are having now the move instruction, multiply instruction, right? Then we are having move negative instruction, move negative, that is we already discussed in the ARM instruction set, right? Then we are having now the negate. So we are having now R0, we are negate that R0 is, we are having now that one as R0 value is going to have as minus R0, negate R0. Then we are having R operation, bitwise R operation. Then we can pop from the stack and push from the stack, push to the stack the content, rotate right, subtract with borrow. Then we are having stored multiple instruction. Then we are having now that store single register, subtract instruction, then software interrupt instruction, and test single bit instruction. We can have test bit instruction. So here these are all the instructions, right? So around we are having now 32 instructions. I think so 32 or something. You see. So these are all the thumb instruction, right? So thumb instruction is limited one. So we are having now add with carry. So add two 32-bit value and add with carry. Next we are having now add, just we are having two 32-bit values add. Instruction is 16-bit, right? But here, so we are having that instruction is add R0, comma R1. So this is equal to R0 equal to R0 plus R1. So this is we are having that instruction. So instruction is 16-bit, but R0 register is 32-bit, R1 register is 32-bit. These two is added, the 32-bit result we are getting now. So that is we are having now add to 32-bit, right? So here add with the carry. So we are having now the carry flag register also we are adding now. Then logical bitwise AND operation, arithmetic shift right, ASR, branch, right? So we are calling the branch without condition. We are having branch relative. Then logical bit clear. One particular bit we can make it as clear. So for that we are using now big pick insertion, right? So bit clear insertion. Breakpoint is if you are having a program, within that program we can temporarily stop one location, then we add one insertion called PKPT. If you are adding this instruction, if you are executing, it will execute until the breakpoint. Then it will wait. Then after that, if you are making that once again you continue, then it will continue that instruction. So wherever you want, you stop that one, you make the breakpoint under the like we can execute a part by part of the program, and we can check whether it is executing properly or not. We can check now. For that, we are having breakpoint. Next one is branch with link. Branch with link is we are having now the branch with link with the particular label, then it will store that link register content with the next location of the branch with link, and then it will go for branching to the label, where the label we are having a subroutine, and then we at the end we are having return. The return will go to that link register content. The link register content is where we are calling, then it will return to that particular next statement. So for that we are having now link register. So link with the exchange. Exchanges we are having now thumb instruction to ARM instruction we are changing now. So that is called PLX, right? So we are coming from the ARM thumb instruction program where we can call that one subroutine. The subroutine may be ARM instruction subroutine. Then we have to convert from thumb to ARM. That is we are doing the exchange. So if you are calling that the instruction is ARM, then we need to have exchange, right? Then branch with only exchange. Just you no need to return that one. So for that case, you can use branch with exchange. And then compare negative. Compare negative is we are having now CMN with R1 and R2. Then it will do that R1 plus R2 operation. What is the result? The result is going to affect the flag register. That is compare negative. Okay. Right? Then we are having compare negative. Compare is it will do now R0 minus R1, and what is the result? Then it will change the exclusive OR operation, right? Load multiple register, LDM with R0 exclamation symbol, then we can have now the number of registers R1 to R12. We can do that one, right? R1 to R12 we can do that, right? Then we are having now compare negative, exclusive OR, LDM, load multiple, load single register. Then we are having logical shift left, logical shift right, and move, right? So move is we are having moving from one register content to another register content, right? So the logical shift left is here R0. So we are having now we are writing that instruction is we are having now logical shift left with the R0. Here we are having R0 comma R1. So it will do now that the particular R0 is going to have the logical shift left with how many number of bits. So that R0 is going to have logical shift left. We can have now logical shift right also is there, and we can have now the move instruction, multiply instruction. So multiply. We are having now mul with the R0 comma R1. So we are getting now the result is R0 equal to R0 into R1. We are getting now multiply. Right? Move negative. So we are moving from one content to move negative as MVN with the R1, R2. So R2 content is going to be negative and we are moving to R1. So that is R1 equal to minus R2. That move negative, right? So we are having the negate that number, right? So negate with the R naught. So R naught is going to make it as R minus R naught. Negate, right? Then exclusive the R operation. Then we are having popping that in from the memory location to the register. Pushing now from the register content to memory location, we can push it now, right? Memory location is not memory location. Using the stack pointer, we are having a stack pointer is one register where we are having an address. This address is located at one particular stack, right? So this is we are having a stack. Then the stack pointer is here. Then stack pointer is recruiting and placing the data in the stack, right? So if you are popping now, it will take now as incrementing that stack, right? So we already see that one. We are having another stack with something. Here we are having only one effect, right? So we are having now that of multiple registers from the stack. Pushes multiple registers to the stack, right? Then rotate right. Subtract with borrow. Subtract with borrow, right? So with carry is subtract. In that subtract we are having with borrow. STM store multiple, right? So we are having now the multiple register, we can store it now. The store single register, subtract, then software interrupt, then we are having now the test fit instructions. Like we are having now around how many number of instructions? Right, around 31 instructions. Right, now we'll see in detail about the instructions. Now we can access the registers R0 to R7 we can access by all instructions. R0 to R7 we can access by all instructions. Then R8 to R12 only access for move, add, compare negative. So this is another restriction in the thumb instruction. So we can use that only R0 to R7 registers for all instructions. Right? This R8 to R12 we can use only that move, then add and compare. So then we can have now that's add with carry ADC. ADC is not using that other registers. Only R0 to R7 we can have. 8 registers are there. So we can use only that 8 register for all other instructions. So 8 to 12 instruction registers we can use for move instruction, add instruction and compare instruction. So that is we can. We can have now R13 is already know that one stack pointer, R14 is link register, R15 is program counter, then we are having CPSR, SPSR. So this is actually summary of thumb register usage. So thumb registers we can use in that rules only, right? In that restriction only we can use the thumb instruction registers, right? So all instruction can access R0 to R7. The move, add, compare only can access more than that R7. R7 we can access and also R8 to R12 we can access, right? Then we are having here a stack pointer, link register, program counter are limited accessibility. CPSR only indirect access. Then SPSR is no access, right? So SPSR is not possible for the thumbs. Now we will consider now arm thumb interworking. This is another important concept. Arm thumb interworking. Interworking means I told you that one from the arm to thumb we can exchange, thumb to arm exchange. While doing that exchange, we can have branch with link and exchange and branch with exchange. We are having two types, right? Branch with exchange is just it is moving now. So we are having now from thumb version branch exchange, right? So here we are having branch exchanges. We are moving that arm instruction to thumb instruction or thumb instruction to arm instruction, right? So that is we are having the last bit. The R0 of that 0 is used for changing that instruction. So whether it is arm instruction or thumb instruction means we are having T is 1 or otherwise it is having 0. Right? Now branch with link and exchange, right? So what it will do now, branch with link is it will store the next instruction address in the link register, and then program counter is loaded with the label. Label is here PLX with one memory location, that is called label. So where we are having now, if you are having the branch in some other location, so this is the label. Label is nothing but one location. So branch to that location. Branch with link with the exchange means then it will save the next instruction address. So this is address 1 A1, then this is address 2. So this address 2 is saved in link register, and then it will go for executing that label, and at the end we are having return address. The return address is taking that value from the link register content to once again the program counter. Now the program counter is instruction is execution is moved to this location, right? So here we are having now this label is going to be loaded with the program counter, then automatically your execution is going to link with that location. So continue that one, right? So that is here. PC with the label. If you are having that arm to thumb exchange, then we are doing now the thumb instruction change. Otherwise, we are having now thumb is 0. Then after completing that one, then the program counter is going to add that value, right? So we are having now that one. So it is doing some other operations here, and then at the end we have to complete return. While return, the PC is going to be loaded with whatever in the link register we are storing now is loaded. Now the instruction is going to execute. So that link register is having A2. So A2 is loaded in PC. So if PC is loaded, now the execution is returned to that location, right? So that is we are having now as arm with thumb exchange. Right, now here you see this one, how do you exchange that arm thumb, right? So now we are executing that one. Port 32 is arm mode, right? So this is where align. Then we are having now that from the arm mode here we are having now LDR R0 the thumb code plus 1, right? So thumb code is here, then plus 1 is we are having now this is loaded in the R0 register. So this is the location. We are adding that one, so that one is here we are having now. Then move PC to move PC to LR. So that is we are having now PC content to LR, and then we are having a branch with exchange to the location R0. So this is we are having now. It is going to have that one execution, right? After execution, then it will return to link register. So that is we are having link register to PC. PC content to link register is loaded. So now the link register content is revert back, and it will move to that where we are having now that call, right? Then from that one we are receiving, right? So that is we are having now the corresponding. Then if you are executing thumb mode, then we are having the letter capital letter T in that location of CPSR. So that is one thumb execution. Right. Now we are having now this one as we are having now branch with link and exchange with the R0. R0 is the locations. We are having thumb plus 1. So here this is the location, right? Then it will go for that execution here R0, and then we are having now this is we are going to do that one after completing that one, right? So we are having now the branch with link exchange R0 thumb code, right? Then we are having now thumb code instruction is we are adding one, and then we are having the R14 is link register content. Link register contents we are having return to arm code state. So this is thumb code execution. Then we will return back to, it will come to that one through the conversion of arm code, right? So return to arm code. Now in the 16-bit the branch instruction, right? Branch with label, branch with link, right? So branch with label, it won't save that next address, right? So just we are branching, right? So we are having some program Here we are having now branch with some label. Label may be in somewhere else. Then it will continue the label instruction, and there is no return. So it is branching now to that location. So it will continue now. It is skipping that set of statement, right? So that is branch. Just we are branching now, right? So if you are having branch with branch with link is we are branching that instruction, then the link list content is loaded, and then it will execute that branch instructions. Then we are coming with a function call as like, then at the end we are coming return. Return will go to the link list content, and it will move to the next where we are calling the next statement onwards. It will continue now after completing the routine execution. Here we are having now that these three statements are equal. What it is now, link register content move to program counter. So link register content move to program counter is return, right? So we are returning that. Then link register content, whatever the link register we already saved, is moved to PC. Now that instruction execution will go to the address saved address location, right? Then we are having this another one is branch with exchange with LR, right? So LR is here we are having now link register content. We can have now. So while return that one, then we go for the link list. Or otherwise we can have now pop PC, right? So pop PC is program counter whatever the content, then the content is going to be pop. Then we are getting now this is we are having now return, right? So we are using the subroute stack. We are pushing now while calling. Then after return back, now we are popping now. Popping to PC, right? So,
बट ज्वाइन कर लेना क्या हो जाएगा
hello.
इससे आवाज नहीं आएगी देखना 8 बजे चल रहा है
Hello. Ari, mute yourself. Okay. Right. Right now the data processing instruction, right? So that is we have seen that one. Add, then we are having now these are the possible instruction: add with carry, add and fit, exclusive or move, multiply, move negative, negative. Then we are having OR operation, subtract with carry and subtract, right? So we are having now two registers for all type of instruction. We are having now two registers, right? So this is a register. Then we can have now RD. So we are having now that instructions. Similarly, here we are having now the arithmetic shift and something with that immediate, right? So that is we are having now arithmetic shift register content, and we are placing that content into that register. Then add, move, subtract. So add, move, subtract, we are using now that RD with the direct immediate value. Next one is add and subtract is we are having three registers. Then add, we are having now two registers, and then we are having one more direct value. Add to register one more direct value, and add and subtract with the stack pointer with direct number. So stack pointer address we can change. And then we are having arithmetic shift right and logical shift left with two registers, right? So this is we are having now, this is logical shift left with the content with how many number of bits we are going to have now with the RS. Similarly, we are having compare negative, test bit, then we are having now that RM and RN. RM and RN. Right? So that one as you will see. So what it will do now, add with the carry. So we are having RD and RDL itself, then plus added, then carry. That is I told you that one. So RD, RM, right? Then add instruction with that one. So we are having RD, RM with immediate data. We can have now the direct insert one more register. We can have now the direct value, right? So that is we are having now R0, R1 hash 10. So that R1 content added with the 10 and placing it in R0. So that is we are having R0 plus direct R1 only. R1 hash 10. R1 plus R1, right? So that is well. Then two register content and place it in destination. Then we are having two registers and we are having placing, right? So like we can have now that set of instruction. If you are having the stack pointer content is added with, then we are having now the bitwise shift left 2. So this is equal to multiplied with 4, right? So why you need to have multiplied with 4? Each one is word. So each word is 4 byte. So you have to multiply with the 4 times. Then only the stack pointer is first stack pointer. We are taking now the data, and second stack pointer is more the 4 bits later, right? So another one next pointer 4 bits. Instead of that 4 bit, just we are having now the shift right. Shift right is we are having multiplied with 4. Now bitwise AND operation, right? RD equal to RD and RM. So two registers we are using now. Then RD and RM is AND with. Then the result is going to place in RD destination, right? Then we are having arithmetic shift right. So RM content we are doing the shift right. Then we are placing now that register, right? And also it will add now the carry flag, right? All carry flag we are setting now as we are filling with the carry flag. Arithmetic shift right? So if you are doing the right operation, then the carry flag is continuously filled at the end. Then only we can get the corresponding bit. There is no change in carry flag. Right? Logical bit right and logical bit left, everything is there the same manner. Right? We are having that multiply, right? Multiply and RD and RM, we are placing the data into RD. So this is 32-bit only result. Then move the logical NOT, right? So the NOT value, and we are moved to some other register. Then we are having negate. Negate is that one, 0 minus RM. So we are getting now minus RM. Then R operation, RD or RM. Then rotate right. RD, right rotate, and RS. So we are getting now the result in RD. And also we are C flag registers, we are having RD minus RS minus 1. So the RS is the total register minus 1. So that one is most significant. Right. Next one is subtract with carry, right? RD minus RM minus not of the carry flag. So 1 means then we are subtracting, right? Then subtract two numbers. The direct value we are subtracting, and RD minus direct value we are subtracting now. Then RN minus RM we are getting now that is some other separated, right? Stack pointer, the stack pointer minus immediate 4, right? So the stack pointer is going to shift now. So stack pointer is going that 8000. Next it will go to 8004. If you are going the stack pointer is downwards, then we are having now 7FD. Right? So that is we are having now the corresponding address. Right. So same one is repeated now. Now this is thumb mode instruction, right? R0, R1 and R2. Only thumb mode instruction, not more than that size. So we are having the logical shift left with R2 and R4. So how do you do that one as R2? Then R4 is only 1 bit. So R2 is already 2. So it will shift left, it will multiply by 2. So we are getting now that value. That is already discussed in the ARM instruction set itself. So the registers load and store. So thumb instruction. Then LDR, STR, byte, half word. Then we are coming without that byte half word, then it is full word, 32 bit, right? So LDR or STR with byte, right? So that is here LDR byte. So only 1 byte is loaded into the registers, right? Then LDRH 2 byte is loaded. LDR is 32 bit, right? Where is implied. No need to tell that one. LDR is 32 bit. STR also 32 bit, right? Then we are getting now that LDR and STR. Logical shift right. Then we are having now the store registers, load register with byte, the store register with byte, then load register with half word register load, then stored register with half word. Then we are having now sign, okay, right? So we are having sign byte, then signed hardware. Right. Addressing mode, direct mode, indirect mode, then indirect with offset, then we are having now a relative addressing mode, right? So we are having, these are the types of modes in the thumb instructions. So we are having multiple registers, LDMIA, STMIA, right? So the same way as in the ARM instruction, STMIA, right? Stack pointer is push and pop, right? So here we are having push and pop operation is there, right? That push and pop operation is there. So we can push the set of register to, then we are having that register list in the using a program counter. Then pop the link register content. So we are push the link register content with the link register address. Okay, push and pop. Now the software interrupt instructions, right? So we are having now the software interrupt with the immediate then particular value, right? Then what we have to do is link register with we are having now supervisor mode. Link register is address of the instruction following, right? So the following instruction address is going to be loaded with LR link register. This is address L1 loaded with link register, right? Then we are having CPSR content is going to be in this supervised mode. So we are having now the supervised content. Then a program counter is added with that vector plus 8, right? So what is the current location? Then it will add further 8. Is the PC, right? Then CPSR mode is we are having supervisor mode. CPSR interrupt is we are having 1, right? The CPSR T is 0. Right? The CPSR I, right? So CPSR is 1 register. The interrupt register is going to make as 1, right? So we are putting now the mask. Then we are having now the CPSR with T. So we are having now the T type. Thumb mode, right? So we are having now ARM to thumb state. So this is in the thumb state only. Okay. So these are all the thumb instructions. We can stop here. We will continue by next class. So these are the thumb instruction set, right? So they may ask question as ARM instruction set or thumb instruction set, or how do you do that ARM thumb interworking? So from ARM mode to thumb mode, how do you exchange? Thumb mode to ARM mode, how do you exchange? We have to do. That is ARM thumb interworking. You have to give the example. Right? So here we can stop here. So we will see that all thumb instruction set. The thumb instruction set is subset of the ARM instruction set. Right? So in that syllabus we are having now that ARM and thumb instruction. So instruction set of the ARM processors we are having ARM mode and thumb mode. Right? We can stop here. If you are having doubt, you can ask now.